Good morning, everyone. We begin our real analysis lessons or series today. I'm going to begin with a quote by Gottlob, the German mathematician Gottlob Frege, spelled Frege, and his first name was Gottlob, Gottlob. And I wrote down the quote, and I really think the more I read Frege, the more I feel more in tune with his way of his approach for systematic mathematics. And he wrote the following. He said, "Every good mathematician is at least half a philosopher, and every good philosopher is at least half a mathematician." So we really need to talk today. A lot of you are not familiar with who he was. So we got to talk a little bit about first, introduce you to the way he's thinking. And he wrote a book in 1884, and he really had a groundbreaking view on numbers. It was called The Foundations of Arithmetic, 1884. And what are some of the main ideas in the book? The first one is that numbers are seen as logical objects. So Frege argued that numbers are not psychological or empirical entities, but they are objective logical objects. He rejected the idea that numbers come from experience or intuition. Then you have the context principle. He emphasized that one should not ask what a number is in isolation, but rather how it functions within a proposition. He famously stated, by the way, where's the quote? I have several of his quotes actually that I wrote. He asked, never ask for the meaning of a word in isolation, but only in the context of a proposition. That was the question he was asking. Only in the context of a proposition. And then you have numbers that are seen as extensions of concepts. Frege defined numbers in terms of logic using set theory, which is what we've been doing on this channel all along. He proposed that a number is the extension of a concept. And what that means is that the number associated with a concept is the collection of all things that fall under it. For example, the number 2 corresponds to the concept of being a pair. You know, he was really relying on a principle that is often attributed to David Hume. David Hume was also another philosopher. The number of F's is equal to the number of G's if and only if there is a one-to-one correspondence between F's and G's. And that was really central to his logicist project, which aimed to define arithmetic purely in logical terms, as it should be. So there's an element of logicism here because Frege believed that arithmetic could be derived from pure logic, meaning numbers and mathematical truths were not separate from logic, but were logical truths. And this idea influenced later philosophers and logicians, including Bertrand Russell, by the way, who was like the unwelcome house guest, and Alfred North Whitehead. But of course, we have to acknowledge that Frege's system ran into trouble due to something called, and I'm sure my audience now, if you're watching this series, I hope you've heard of Russell's paradox, which exposed inconsistencies in the logical foundation. but his contributions laid the groundwork for modern logic and really a philosophy of mathematics. But yes, you should be aware of Bertrand Russell wrote a letter to him, and he found a crack in the foundation. But the way I see it, because people have often asked me about it, and the way I see it is I agree with David Hilbert. And Hilbert himself, by the way, Hilbert, interestingly enough, grew up in a Lutheran home, a Calvinist home. Later on, he became an agnostic, but he had the same kind of spiritual Christian. All of these men had the same Christian foundations, at least in the Western world, that we've been defending on this channel. But David Hilbert, he said he was a leading advocate for the formalist approach to mathematics. And he acknowledged that the seriousness of the paradox, but he remained optimistic. And I remain optimistic as well, that a properly constructed formal system could resolve the issues. In fact, he famously declared, and I love the quote, he said, "We must know, we will know." You also have later on Henry Poincaré. Poincaré, I hope I'm saying it right. Forgot my French. I used to study French, but I don't practice it. And Poincaré saw the paradox as evidence that set theory was leading mathematics into dangerous territory. So you had the other point of view. He was really skeptical of the logicist program, and leave it to the French to be skeptical. And he viewed paradoxes like Russell's as a sign that really that unrestricted set formation should be avoided. I don't agree with Poincaré on that. But I was also interested in Alfred North Whitehead's opinion. They spent years, he along with Russell, they spent years trying to resolve the paradox within the framework of their Principia Mathematica. And their solution involved, they introduced type theory, which prevented self-referential sets from forming in the first place. So it really did cause a crisis in the foundations of mathematics, but it also led to significant advances in logic, set theory, and formalism. You had Hilbert, Zermelo, and eventually Gödel trying to redefine and rethink the mathematical foundations. But really, what is a number? It's a simple question, and it has sent the finest minds of mathematics and philosophy into spirals of paradox and revelation. So I'm going to try to do my best to sort of give you a foundation in this video of what it actually is. So we'll be discussing the properties of numbers and all of that. And what is a number? So we have the classifications that you normally learn in higher level math, or at least, and you should be learning this, by the way, even at the middle school level, the different kinds of types of numbers. First, we have the natural numbers. And those are what most people refer to as numbers. Those are the counting numbers. If anything is going to be a number, this is it. Then we have the integers. And I included a quote here by the great mathematician Leopold Kronecker, who was he was born a Jew, but during the last year of his life, praise God, became a Christian. And he once said, "God made the integers. All else is the work of man." He had some conflict with other mathematicians who were not spiritual, or at least who didn't share that mathematics is an objective truth that is the result of a creator. Then you have, and by the way, the integers, just to be clear, if you're new to this channel or you're new to this whole concept, integers are whole numbers, including zero, that are positive and negative in that case. Then you have the rationals. And the rationals, they have certain interesting properties. They are, well, one of them, they are nested. And between any two rational numbers is another one. And between any two, there are infinitely many others. They are also closed under addition, subtraction, multiplication, and division. However, you have to be careful with division, right? I gave an example here. If P and Q is an element of the rationals or of the rational numbers, then P plus Q is also rational, and so on and so forth. If you multiply them, you also get rational. However, you have to be careful with division. As always, if you divide P divided by Q, of course, you cannot have Q cannot equal 0. But that being said, the rationals have problems. I want you to pause the video for a moment and think about what potential problems could there exist with the rational numbers. What are the problems associated with the rational numbers? All right, so hopefully by now you've been thinking about the implications here. We asked, what are the problems in the rationals? Well, it's possible that P can be rational, but yet the square root of P is not, as we all know. For example, in the square root of 2 is not a rational number. We'll get to that in a moment. It also has lots of holes. It's possible that, for example, when you have a sequence, it converges to some P that is not a rational number. Also, they are not algebraically closed. You've got polynomials with rational coefficients whose roots are not rational. There's an example of one here. F of x equals x squared minus 5. The reals will only partially solve this problem. So that's why you need the complex numbers in order to have algebraic closure. So when you start to fill in the holes, you will notice that most numbers are not rational. And that brings us to our next discussion, the Pythagorean Theorem, and a little bit of history here because it gets better and better. All right, so we really have to discuss the Pythagorean Theorem. Take a pause for a moment. Just think about it. Most of you, if you've been awake and you have some kind of a pulse, you probably, I hope, you've heard of the Pythagorean Theorem in school at some point in your lives. And the theorem tells us a squared plus b squared equals c squared when you have a right triangle, for example. And the theorem is really significant, not only for its own merits, but also because it really is the key to proving that irrational numbers exist. And sadly, despite having the key, Pythagoras lived and died. He really did believe that all numbers were rational. When he died, in fact, his school of thought was called Pythagoreanism, and it lived on. And about a century after his death, you had a Pythagorean named Hippasus. And he proved the famous thing that the square root of 2 is irrational. Now, legend has it, the common lore is that the Pythagoreans, they were so horrified by this theorem that they took Hippasus out to sea and threw him overboard, murdering him, killing him, drowning him. They made a pact never to tell the world of his discovery. Can you imagine that? And some truths are too wild for the mainstream to handle. But those who stand firm in their convictions and proofs, like Hippasus in that case, will always be the ones to break new ground, whether the world's ready for it or not. It must be one of the world's worst cover-ups in history because most people know, at least have heard of the Pythagorean Theorem. So let's get into it. All right, so we set out to prove that the square root of 2 is irrational. And the square root of 2 is when you have a right triangle and you apply the Pythagorean theorem, you get 1 squared plus 1 squared, which equals 2, and then you take the square root of 2. So we can begin our proof by saying, well, if radical 2 is a rational number, then it has to be represented as P over Q. And I'm assuming, by the way, the P over Q, of course, is reduced. This is really a classic proof. By the way, is this this is typically viewed as a proof by contradiction. But is it? In other words, what it means to be irrational is that you are not rational. So, is this in fact a direct proof, or is it a proof by contradiction? I'll let you think about that. So we have the square root of 2 equals P over Q. And I'm, of course, assuming P over Q is reduced to simplest form. And then if we operate as usual, if we multiply by Q on both sides, we have the square root of 2 times Q equals P. Then you have 2 times Q squared equals P squared to get rid of that radical there. And this implies that there's divisibility here by the fundamental theorem of arithmetic, which I hope you're familiar with for this series. And so that means that we can write it this way. And if we start using substitution, notice what happens. We end up with Q squared equals 2 times K squared. And therefore, you have contradiction. You have contradiction. So the Pythagoreans can take that from us. All right, now, the next thing we have to talk about, because we can see from this, the rationals are not quite enough. And they do, but if we say it like that, they do have almost every other fundamental property you would want. And they are what we call, which brings us to our next point, they are what we call in mathematics an ordered field. But first, what is a field? Well, it's a set that satisfies the classic multiplicative and additive properties that you should know and love. So let's look at them. All right, everyone, I bring to you the field axioms. Very important. The field axioms are, you have associativity, you have commutativity, distributivity, identity, and inverses. I want you to think about the following questions. Do the natural numbers form a field? Do the integers form a field based on these axioms? Do the rationals form a field? I want you to pause the video, think about it, write it down or somewhere, think about it. All right, hopefully you've paused the video and you thought about it and you've got some responses. Let's look at the first question, the natural numbers. Well, no, the natural numbers do not form a field. They fail. Look at the fourth and the fifth axioms here, identity and the inverse, the identity law and the inverse law. They fail the first half of the identity law. There is no zero in the natural numbers, as we said. And also, it fails both halves of the fifth axiom, the inverses. There are no negatives in the natural numbers. What about the integers? Do the integers form a field? They almost do, but because in this case, they only fail the second half of the last axiom, of the fifth axiom here, the inverses. Because if you have, for example, if A equals, let's say, negative or 2, we'll say just 2. If A equals 2, there is no integer A to the negative 1 that equals such that 2 times that, let's say, equals 1. So this is not, it's not accepted. What about the rationals? Do the rationals form a field? So yes, in that case, the rationals, if you run through all the axioms here, you will see that they do form a field. And that brings us to we're going to talk about that in our next video. We have to talk about more proofs, the triangle inequality, for example, and others. But really, you know, we really have to be, as I always say, rigorous in this. So, mathematics, when you wield it with precision, really can be as powerful as a blade. It can be deadly, as we saw with the case of the Pythagoreans. If it's in the wrong hands, it can be dangerous. But in ours, it's a tool of truth and precision. We're not merely we mathematicians, we're not merely scholars. We are gentlemen. We're honorable, we're measured and resolute, but we're also rigorous. And make no mistake, when the occasion demands it, we can be as formidable as the theorems prove. Or to put it in slightly stronger terms, if we have to punch your lights out, we will. Have a good day, everyone.